Let's get started on 15.5 on triple integrals. So for triple integrals, the basic format is something like this. And the first way we're going to interpret this is how I have it written here. Is you have a volume, or sometimes we call a solid Q, that you're integrating over. Now we will put a function inside the integrand, and that could represent like density. So if you did volume times the density, you'll get mass. So this is a way to describe that. So another way to interpret this then is integrating over a region R, just like we have done before. So down here will be the region, like that. So there's my region R. So let me change this. Oops. So here is my region R that you're integrating over. So you are basically partitioning that region the same as we had done before. So you go through and you do that partition, okay, etc. And then you have a height, and then you take each one of those, and this isn't a very good picture. They're kind of hard to draw. So take a look at the book on the representative rectangular solid. So it's a parallelepiped or rectangular solid that you are, these little chunks, little pieces that you're adding up. So that you're doing the sum of all the delta V's, so the delta volumes of those little pieces. Okay, and then as before, you take the norm of the partition, which would be the length of the diagonal goes to 0, and you end up with your triple integral. So the triple integral is over a solid, and then you have your function of 3 variables, x, y, z, inside. And we'll get into more of that later. Right now we'll just evaluate and look at some examples. So I'm not going to get in too much more theory on triple integrals. The setup's same as before. There's plenty to do in just evaluating. You take away, and go back here, you take away this function. If you interpret z as f of xy to z as h of xy, that's like the bottom to the top. So in double integrals, it's like you're just taking the difference of those would give you the height right here, right? That's the height of the function. My interpretation here isn't quite right. I just noticed that. So you have your function on top, so you have your base to the height. But if your function below, so we could just do a little diagram here. So if you have some function down here, and then you have another function up top, then you're going from the lower function to the upper function. So you're integrating to that direction like this. And then those are rectangular solid pieces that you're adding up. Okay, so let's take a look at some examples. So I went ahead and wrote down a few examples this time, and we'll do some more as we go. We'll be erasing these as we go. So, so here's the first question, kind of the first simple question. You're evaluating the triple integral over the solid Q, and then some function. So that's the integrand. This right now it's just like you're multiplying numbers. Doesn't really mean anything necessarily. All right. So this function though is like a 4-dimensional function. So it's f of x, y, z. It could represent like density at a point, which will make sense for the mass and density questions later. In this case, your Q is just a rectangular solid. So you're going from -1 to 1 on your x, 3 to 4 on your y, and 0 to 2 on your z. So when you integrate, your integrand is the same, so let's go ahead and get rid of that. Okay, so there's your integrand. And then your limits of integration, you can do this in any order because they're all constant limits of integration, right? So that's constant limit of integration, right? All of those are constant limits of integration. So the order doesn't matter in this case. When it starts to matter, you'll have functions of different variables, and you have to do the right order. So that's the setup. Go ahead and try that from there. First integrate, and so now you have to get your mind going that you're integrating with respect to the different variables and holding the other variables fixed as a constant. So before you're differentiating, now you're integrating. So it takes a little bit for the mind to work so that you can picture that. And you maybe haven't integrated in a while either. So, so look that stuff up and spend some time on just integration. Always takes me a little bit too to picture it when I first do this stuff after half a year of whatever. All right, so do that integration. Go ahead and pause it, and then I'll unhighlight what I have. First one there, and I'll go on to erase everything. Second one, and I didn't do the rest of them. Or I didn't actually finish the last details. Looks like the answer I got here is 28. Okay. So, next one. Sometimes the questions will be setup only because there's a lot of work that can be done for the integration itself. So go ahead and write this one down. This one's a setup only. Don't have to evaluate it. So set up a triple integral, so it specifies that, right? To find the volume Q, where Q is a solid in the first octant bounded by the coordinate planes, right? So that's just, the first octant side of that. The function z equal to 2 plus x squared plus y squared. Okay, so that's like f of x, y. So that's like a function. And what you should be able to visualize what type of function that is right away. Right, paraboloid, open up to 2 units. And then the cylinder, right, so if it's a cylinder, we are assuming that z is then arbitrary. So it's a circle, and then it goes up to the cylinder. So you want to graph, you always want to do your 2D and 3D graph. So first we'll do graph in 3D here. Okay, we'll do that right below. And I already got, it's not a very good one, but check that out. And then you want to graph in 2D or vice versa. So you have your base and you're going up to the surface. Okay, so go ahead and graph this. Take away those, okay. So there's my paraboloid, z equals, and then that's the 2 plus x squared plus y squared. And you can see you have your base below. So you're going from your base up to the surface. So you want to be able to, so the volume you're looking for, you can see is not, it's an irregular surface, right? Because you have the curve up here, that's the paraboloid. So you want to put in your representative rectangular solid piece, which is here. And you're integrating from the base, which is, now that's z equals. So you're going z equals the base, which is here, up to the surface. And the surface is, of course, that. Now, it's in the first octant. So it's only out here that you're integrating. So when you draw in 2 dimensions, so x and y, you just are looking at this piece. And you can integrate from around that little piece. Now later we'll convert this to probably polar or something we'll call cylindrical, or we'll do something called spherical coordinate systems. That's a little later. But for now, it's just setup. It doesn't matter what it is. So we're going to integrate around that. So it's from y equals 0 to y equals the function. So the function is the top half of that root. So you would solve this equation for the root, right? And then you add those up from 0 to 1. So remember that you always have to have your outside limit be constants. So the outside has to be the 0 to 1 or something else, but in this case, that's what we have. You could have solved this for x and says x equals the root 1 minus y squared, and you'll still go from 0 to 1 on the outside. So try to set up your limits from your base, z equals your base, to z equals the function, and then y equals 0 to the function, and then 0 to 1. You set that up, see what you get. And should get something like that. And so you want to picture what it says here, that this is z equals and z equals. That's what it's saying here. And then y equals 0 to y equals. And then last is x equals. And you can put those in if you want. I like to put those in sometimes to picture the order that you're doing it. So that's a typical setup question. And now it's just kind of building on this concept to do more and more. Okay, so let's continue. I have another question. This one I don't have written up. So we'll write this one up. Takes a little bit of extra time, but that's okay. So find the volume. So let's write this here. So find the volume V of the solid Q bounded by the cylinder. So let's start with that. So find the volume V of the solid Q bounded by the cylinder, right? And this is the generic concept of a cylinder. Y equals x squared, and then your z is arbitrary, right? The plane y plus z equals 4 and z equals 0. So z equals 0 is the xy plane, of course. I always like to put that down. And so we want to try to sketch what those are to get our to evaluate. So you want your you have your y equals x squared, and that's in the xy plane, and then your z goes up. So you got a picture like a parabola, but then it's a sheet that goes up. And then you have your plane that you can draw, and then of course the xy plane. So let's try that. So draw in your three-dimensional axis. Smooth that up a little bit, like that. Okay, so x, y, and z. And this time I want to go backwards. So we're going to draw this like this. And then the other direction. And down, just to give a little more perspective this time. Okay, so we have our cylinder, y equals x. So you got to picture the xy plane and you draw that cylinder. So it's going to be something like this. So it's a parabola that opens like that. But then it goes up, right? It goes up and down, but it goes up. Think about it as going up like that. And then you have it up here. Something like that. Let's go ahead and cut some of those off. Okay. But then you have it cut off by this plane. So the plane here, y plus z equals 4, you draw that in the YZ plane, and then it goes it goes out along the x-axis. So that's a line that cuts it off. So you're basically up at 4. 1, 2, 3, 4. We'll just put it right there. That's fine. So here, then it goes down to the 4 on the y-axis, which we'll just put it like here. Don't really count it. So then that line looks like this, but then it cuts off like that and like that. So there's your plane. It's not sure how much you can really picture that. So you're going from the base up to the plane. So now we want to draw the 2D over here. We want to draw that 2D case next. So let's draw that. So you have x, y. So you have your parabola, basic shape of your parabola. Let's see, so 2, and it goes up to 4. 1, 2, 3, 4, 1, 1. Trying to just draw this, best you can. It goes to there. Goes to there. -2. And this value down here, that's your y equals 4, where it cuts it off. So it cuts off right like that. So that's the base below that we want to integrate over. So this base is your region, which is the one down here. And so you put in your little representative rectangles here, just like you would in double integrals. That's y equals 4. The function is y equals x squared. So another little hint to do, and this doesn't quite work on this one, but the first integral you put in is the one that has the most variables. Now this one doesn't. This one is, but we can write this as z equals 4 minus y. So you want to picture going from the base here up to the surface. So there up to the surface. So the surface is the z. Something like that. So you want those little representative rectangular solid pieces. So it's from down here, z equals 0 to z equals 4 minus y is the plane. And then you integrate around the region. So this will be my region R. And when you integrate around the region, you say you're going from the bottom to the top. So it's right. So it's y equals x squared, which is the lower function there, to the y equals 4, which is here. And then your limits, your constant limits, which you must have, is what? Right, do you see that? That has to go from -2 to 2 is what you're integrating around. And we have that line because of how it cut off on the graph. So your volume is equal to, and this was an evaluate, but I don't have the details. You can you work on it. Okay, so it's a triple integral for volume. Your function on the inside is 1, so you don't put it, but it's just 1, like that. Okay. So you're going from z equals 0 to z equals 4 minus y. Then you're going y equals x squared to y equals 4. I meant to say earlier, pause it and try it. Oh well. And then you're going x equals -2 to x equals 2. So then you have to have your order right now because they correspond to those limits. So your order will be dz was first, dy, and then dx. So dz, dy, dx. Okay, and then work that out. Try it and work that out. I don't have the details in there. My solutions I have here that I have in my notes are 256 over 15. Okay, so double check that. Okay, so we will go on to do some more questions. So what we're going to do is gotta get some more details, kind of a good toolbox of techniques to do different kinds, which will include cylindrical and spherical and some others, and then we'll do some applications, and then we'll just practice much more, a few more problems. So let's go and stop the video.